What's the reverse? Absolute value of x.
You gotta compress things around 0. You're still gonna do this.
Absolute value.
Okay, your function is
F of x equals absolute value of x. X is irrational. 0. X is rational.
okay. 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 Work. That'll work. So out here, it's the salt and pepper function with a multiplied by x. And inside here at 0, it's 0. Yeah, that'll work. All right, let's go back to this monotone thing. That's fucking so. Oh, here it is. Amanda, why is that continuous at 0?
I don't know.
Well, what do we have to show? Let's walk through this. To show it's continuous, we appeal to the definition, which says, for all epsilon greater than 0, there has to be a delta that depends on epsilon and the point 0. Okay, we know where 0. Such that whenever we're sufficiently close to 0, that is to say, x minus 0 is less than delta of epsilon, then what happens? F of x minus f of 0 is less than epsilon. Less than epsilon. In this case, f of 0 is 0. So all we have to do is show that if you specify an epsilon, you can also find a delta, so that the function variation on the interval minus delta to delta is no greater than epsilon. Would epsilon equal delta be good enough? I think so. Yeah. If you stay within epsilon 0, the most you can travel on a 45-degree line is epsilon away. That happens when you're irrational. When you don't travel up the line, you travel on the axis, x-axis, if you're rational. So you're never more than epsilon away from 0. If you stay within plus or minus epsilon of 0. But that means it's continuous, and continuous nowhere else, right? Design me a function that's discontinuous, has a type 1 discontinuity at 0, 1, and 2. Something simple.
All right, x times x minus 1 times x minus 2 times x minus 3 divided by x minus 4 times x minus 8 times x minus 2.
Yeah, but that's even better. That's 4 points. 0, 1, 2, and 3.
No, I don't have x to do nothing.
Oh, sorry.
X to do here, but not. It's the function f equals x equals 3 whole. If I did that, and I just multiplied by x.
Why did you multiply x?
Just to have a non-constant number.
The graph of this thing is right?
I didn't get as many removable discontinuities that way as you choose.
So,
And in fact, what was it, Rogers formula does something neat so that you don't get those discontinuities.
the interpolation.
Yeah, the interpolation.
Yeah.
Which is why it works.
X minus 1 over n over x minus. There's a function. I've never thought of this one before. Let's see what properties it might have. What's discontinuities look like? This thing. It's an infinite product of ones. So it's 1, except it's not defined in 1, a half, a third, a fourth, a fifth, a sixth, a seventh, right? So is it defined in 0? the southwest.
Wow.
Well, if it's defined by 0, it's just the ratio of minus 1 over n to minus 1 over n, which is 1. So this function is 1 at 0. But 0 is a limit point for the discontinuities of this function. This might be interesting. It's a separate issue.
There's one more discontinuity for approaches.
Well, yeah, it's this thing. It's this thing with these things all stacked up. 0 is fine. 0 is a good value. It's 1 and 0. But these things just all pile up. That's a limit point there. So it has a limit point to all its discontinuities. It has countably infinitely many discontinuities in interval 0, 1. Well, from what you know, would that be a Riemann interval or not? According to Lebe's theorem. Continuous except for a set measured 0. I think that would be a set measured 0. Surround each one of those discontinuities. Are these discontinuities isolated? If you have any two of them, can you find an interval between them with no discontinuities? They're getting mighty close. But what if you're way out there, like n is a trillion, and the next one over is at 1 over a trillion and 1. There's still some space there. It's not much, but there's some space. There's an interval between them. So these things just kind of slamming on and getting closer and closer as we go to 0. But then suddenly at 0, they're not there anymore. That's an interesting function to think about this. It is Riemann integral. And what would be its integral from 0 to 1? Right?
Make count the number of points out.
Are there any, while we're on the subject, since Dave's here, are there any functions where you have a dense set of discontinuities that's still Riemann integrable? Is there a function defined on 0, 1 such that any interval, no matter how small it is, has a discontinuity in it, but yet the function is Riemann integrable on 0? Matt was going to demonstrate. He still might that function. We talked about it briefly. Maybe he didn't catch it. Tomei's function. Wonder how that goes. Burke does an analysis of Tomei's function. Not Tomei. Oh, this one's important too.